Okay, good morning everyone. So we will continue. Today's lesson is still about volume of a solid by plane slicing on your book, chapter 5, lesson 9, page 242. And now we're gonna continue to the next variation of problem set. Yeah, you can open your book, page 244. Now, as a review, I just want to remind you that volume of a solid by plane slicing. Basically, you're gonna have a region on two-dimensional coordinate axis, and then usually it's rotated by a certain axis. And then remember, you need to create a thin rectangle from the region, and then you rotate it. It becomes a slab. And then the previous example is like a coin, really thin cylinder, and then you need to determine the dV. After you determine the dV, you perform the definite integral and then evaluate it from the starting point to the end point. Yeah. So now I'm gonna continue to the harder problem. Example 3, actually some of you have asked that what if there are two functions involved in one problem. Yeah, so let's look at example 3. So it is still about rotate a region bounded by two curves. It's still a rotated problem set, but instead of boundary by one curve, it's by two curves. Let R be the region bounded by the graph of y1 equals 6e power of negative 0.2x and y2 equals square root of x. And by the vertical line x equals 1 and x equals 4. Find the volume of the solid generated by R is rotated about the x-axis. Assume that x and y are infinite. Show that your answer is reasonable. Okay, so example 3. The first y is 6e power of 0.2x with negative. And then the second y is square root of x. And then it's written verticalized x1 until x4, yeah. So x equals 1 and x equals 4. Okay, so let's sketch it first. Well, let's go with the easy one first. Y equals square root of x. You know that this is y equals square root of x, right? Okay. And then 6e to the power of negative 2, 0.2x. Okay. Then the y-intercept is 6 for sure. And then you need to find out the value of y1 when it is 1 and 4. Yeah, because it's evaluated from 1 until 4. Well, when x equals 4, the y2 is 2, right? Yeah. So we want to find out whether if the x equals 4, what is the value of y1? So when I use calculator, 6 times e to the power of negative 0.2, the answer is, this is 4.9. And then if it's 4, negative 0.8, it's 2.7. So basically, until x equals 4, the exponential is still above the square root, yeah. So it's kind of, so this is not really accurate. This is not 6. So let's say 6 is here. This is 6. So it's supposed to be like, kind of like this. Okay. So this is the area. This is the area. Bounded by y1, bounded by y2, and vertical lines x equals 1 and x equals 4. Okay, this is y1, this is y2. Okay, and then rotate it about the x-axis. So you want to rotate it about the x-axis. So on the previous video, I said it wrong. I said that the rectangle that is made must be parallel to the rotating axis. Actually, the rectangle that is made must be perpendicular. Yeah, I will repeat. The rectangle must be perpendicular to the rotating axis. Yeah, so actually you just need one rectangle here because it represents everything is the same. Y1 minus y2 will be the height. Yeah, this is the rectangle and it's rotated about the x-axis. Okay, now you imagine that instead of the rotation is on one end of your rectangle, it has a space. It has a space. Yeah, so it's rotating with a space. Yeah, it means that it's not gonna be a whole cylinder, but it's kind of gonna be like a coin, a disc, a DVD, compact disc. Yeah, it's gonna be like a compact disc. Well, if you wanna see a clearer picture, then you can see your book page for 244, figure 5.9D, the right picture. Yeah, it's a compact disc. It's like a disc. Yeah. So if it is like a disc, then it's gonna be like this. Yeah. And then again, the principle is the same. We need to determine the dV. Yeah, the dV. So the outer, let's say the outer radius is R1 and the inner radius is R2. Okay. So basically, then the volume of the compact disc dV will be equal to dV of the bigger one minus dV of the smaller one. Yeah. Okay. Yeah. So it's gonna be equal to dV. So the bigger cylinder is pi R1 square height minus pi R2 square height. Yeah. And then if you want to define it with the variable, then it's gonna be pi R1. R1 is from here to here, which is Y1. Height is dx, the thickness of your disk. And then minus pi R2 is Y2, yeah. This is R2. Okay, times dx. And then if you substitute, I mean you factor out the y, then your equation, the dv equation will be 6e power of negative 0.2x minus being squared, yeah. I'll just square it by the way. If it is squared, then it's 0.4, yeah. And then square root of x being x, square root of x being squared is x dx. Well, it's supposed to be 36. Don't forget. Yeah, because 6e power of negative 0.2x being squared. So it's 36. And then e power of negative 0.4x. Yeah, I hope you still remember. It's algebraic operation. Okay. And then, of course, the next step is just to integrate, yeah, integrate dv from 1 until 4. Okay, so it's equal to pi, let's put out the pi outside, 36 e power of negative 0.4x minus x dx from 1 until 4. Okay, so it's equal to pi, then 36 36 divided by negative 0.4 e power of negative 0.4x minus half x squared, 1 until 4. Okay, so it's equal to pi 36 divided by negative 0.4, 90 minus 90 e to the power of negative 0.4x minus half x squared evaluated from 4 until 1. So it's pi, let's calculate, negative 90 e power of negative 1.6 minus 8 minus negative 90 e power of negative 0.4 minus 1 minus half. Yeah, and then if you calculate correctly, the result is 34.658 pi. Yeah, so that's how you do it. That's how you find the volume of a region that is bounded by two curves rotating to a certain axis. Yeah, and then next, I will read it from your book, page 245. In example 1 until 3, the figure was generated by rotating a region. Such a figure is given the name solid of revolution. Yeah, because it is revolved, it's rotated to the certain axis. As the strip rotated, it generates a disc or a washer or like a tin coin. Yeah, the same disk or washers would be generated if the solid were generated first, then sliced with planes perpendicular to the axis rotation. As a result, the technique you have been using is called finding volume by plane slice, by plane slicing. Yeah, actually there is another method which is cylindrical shell, but we will not go through it. We will discuss it later at the end of this semester. Yeah, so the method that is used right now is called plane slicing method, volume of a solid by plane slicing. Okay, once you realize this fact, you can find volumes of solids that are not generated by rotation. All you have to do is find the cross-sectional area in terms of the displacement perpendicular to the cross-section. Example 4 shows you how. So on the next example, I'm gonna teach you how to find the volume of a solid where the volume is not, well, when the solid is not necessarily made by rotating a region by the axis. Yeah, but of course there is a certain condition that is similar, that is applied to all value of x, that is applied similarly. Yeah, so now let's look at example 4. Plane slice of a non-circular solid. A 2-inch by 2-inch by 4-inch wooden block is carved into a shape shown in figure 5.9e. Yeah, the graph of y equals 4 square root of 4 minus x is drawn on the black face of the block, so on the back side. Then wood is shaved off the front and top faces in such a way that the remaining solid has a square cross-section perpendicular to x-axis. This is the key word. The solid has square cross-sections. Square cross-section perpendicular to the x-axis. Find the volume. Okay, so example 4. I will draw it two-dimensionally first, yeah. I will draw it two-dimensionally first. So 4 minus square root of x, let's say this is 4 minus, this is y equals square root of 4 minus x. 4, this will be 2. Kebalik. This will be 2, this will be 4. Okay, and then if you see the shape on your book, page 245, figure 5.9e, the wooden block, it was rectangular prism on the left picture, and then on the middle, it is carved into a solid with curved sides, so it's gonna be that shape. And the rule is all the cross sections that is perpendicular to the x-axis is a square. It's a square shape, yeah. So perpendicular to the x-axis. So you see the slab. If you see the slab, then of course, first of all, I will create the rectangle. Yeah, that's your thin rectangle. And then instead of rotating it to the axis, then it says that your rectangular shape, if you draw it two-dimensionally, your thin rectangle will create a square like this into the z direction. Yeah, if this is x and this is y, then it will create a square into the z direction. Yeah. And then the thing, then what's the shape look like if I draw it? If I try to draw it, then it's gonna shape like this, right? And because it's a square, so the length of this side will be equal to the length of this side. So it is actually a rectangular prism with the base of a square. Yeah, and of course the length, if the side is y and y, and then of course the thickness is dx. Yeah, in this case, then the dv will be equal to y times dx. Volume of rectangular prism, right? Base times height times length. So it's equal to y squared dx. So in this case, the dv is equal to y squared 4 minus x dx. Yeah, I hope you understand. So then the volume is basically the integral from 0 until 4, yeah? 4 minus x dx. So the volume is equal to 4x minus half f squared divided from 0 until 4 is equal to 16 minus 8 minus 0 minus 0, yeah? So it's equal to 8. Yeah? And of course, it doesn't have a pi because it's not a circular solid, right? It is not a circular solid, so it doesn't have the pi. So yes, the answer is 8. If you want to see your book. Okay? So that's the application, that's the example that I can teach you. And then after this, I'm gonna give you a lot of practice. So you should be able at the end of this lesson, by a few meetings ahead, you should be able to find the volume of a solid by plane slicing method. By first sketch the graph, and then determine the solid, whether it's a coin, a tin coin, or is it a disc, or is it like a very thin rectangular prism, or whatever the shape is. And then you need to be able to determine the dv, and then execute the definite integral, so you get the v by fundamental theorem of calculus. Okay, that's all. Thank you.